Up to this point, we have described vectors and matrices from a very algebraic point of view. As it turns out, both of these concepts actually have geometric interpretations, which allow us to more easily understand what exactly they are, as well as how to work with them. So let's start with vectors, okay? Recall that a vector, and we're just going to assume all of them are column vectors. We've already assumed that a column vector is a collection of numbers where each number is placed in one of n positions here. Now, we actually refer to this as an n-dimensional vector because it has n dimensions. And for any dimension I, for all dimensions I in 1 to n, we assume that the numbers are in the real numbers. You can restrict this, of course, to be a smaller subset of the real numbers, but this is typically what we do. We assume that the number x comes from the real number line. Well, if this is the case, then as it turns out, one vector actually represents a unique point in space. That is, it's similar to this. We have an n tuple, and each position represents a particular dimension on one of those lines. So for example, if we had vectors of 2 dimensions, then here's dimension 1 and here's dimension 2, or vice versa. So if we have the vector, let's say 1, 2, then what this says is the first position represents where we are on dimension 1, and the second represents where we are on dimension 2. So on dimension 1, we go 1 out, and on dimension 2, we go 2 up. And the vector itself is a straight line, and we draw an arrow. So the way we think about vectors, at least geometrically, is that they start from an origin, and it's an arrow that goes out to that point in space. So that's the geometric interpretation of a vector. If we had 3 dimensions, x1, x2, and x3, let's say. It's supposed to be a straight line, but it's not. And we had the vector 1, 1, 1. Geometrically, this says we're going 1 unit out this way, and then 1 unit out this way for the vector in 3-dimensional space to be an arrow that goes out from the origin. Okay. Here's another one. Where we go 1 unit this way, 1, 2, 3 units this way, and 1, 2 units this way. So we have that vector looking like this. Okay, so that's our 3-dimensional space there, and that's basically what the vectors look like in 3-dimensional space. Now, 4, 5, 6, 7 dimensions and so on, that's a little more challenging to have a visualization in our head, but still, we get hopefully you can get the point just from the 2 or 3 dimensions. Now, as it turns out, vectors and the operations on vectors have specific interpretations. So for example, suppose I have 2 vectors here. On vector 1, I have this as, let's say I have, this is vector, let's say y, and suppose this is vector x. So what does it mean then to add vectors x and y. Well, we already saw that the way we add these things, we have x1, x2, and that's y1, y2, and we just get a new vector with x1, x2, and y1, y2. But as it turns out, this has another geometric interpretation, the addition at least. Start here, and basically when we add the vector, what we're doing is taking the the source. This is the source and this is the sink of the vector, origin, destination, however you want to see it. What we do to add is basically we shift the y vector and put its, and actually given the tools I have, I can actually illustrate this as such. If it would let me highlight. So when we add vector x and vector y, what we're actually doing is shifting it up so that the source of y, okay, is at the sink of x. The origin of y is at the destination of x. And then what we do is geometrically we draw the vector, the addition of the vector from the origin to wherever y is pointing. And by the way, to prove that this is commutative, you can just swap these and you'll see you get the same point. Cool stuff, right? So geometrically, all this represents is a shifting of vectors to get new vectors. Now, if we put a minus sign, we actually switch the direction of the vector. So if we had something like x minus y, right, then what we would actually do is here's the vector y. We would actually try to see if I can go the other way with it. So the minus of the vector would look like that. And so when we do x minus y, then we actually get that. And we get the resulting vector there. So that's how we think of addition, at least in terms geometrically. So addition geometrically between two vectors is just nothing more than a shifting of the vector itself. Okay, now, what about scalar multiplication? Well, let's think about that. If we have a vector x, where it's determined by x1 and x2, then a vector kx, as we said before, was just k times x1 and k times x2. I messed that up. So what do the scalar multiples look like? Well, the scalar multiples, if I have a vector, here's my vector x, right? And let's say I double it up. That means I'm doubling it up going here, right? And vertically, I'm doubling it up going here. And then as it turns out, when I draw the vector, okay, so this is x, this is 2x. You'll notice that the vector 2x falls on the same line. If I were to draw a full line, rather than just a segment, but a full line out to negative and positive infinity into space, you'll see that the scalar multiple of a vector is nothing more than just taking this vector, okay, taking this vector x. The scalar multiple is nothing more than just taking this vector and doubling it outward that way. If we divide it, okay, I'm sorry, if we multiply it by a negative number, then it's going in the opposite direction depending on how much we multiplied by that negative number. Okay, so scalar multiplication represents an extension or a contraction or a complete reversal of the vector, but the vector is remaining on the same line. Now, one last concept to close out vectors, at least in terms of their geometric interpretation, is that vectors, we can consider a whole set of vectors. So for example, suppose I have just the line, the straight line that looks like this. I have an infinite number of vectors that fall on that line. For example, here's one vector that falls on that line. Here's another vector that falls on that line. Here's another vector that falls on that line. So as it turns out, a line, at least in two-dimensional space, and this is true of n-dimensional space, lines compose of is nothing more than a collection of vectors. That is, to define this line, we know that the equation of a line is y equals mx plus b. If I just call that x1 and I call the y basically x2, I'm saying x2 is equal to mx1 plus b, okay? So what I can say is consider the line itself is the set of all vectors x1 and x2 such that x2 is equal to mx1 plus b. And that defines a vector. Now, what's interesting about this collection is that if I take two vectors from here and I add them together, I get another vector that's on that line. Try it, right? Take this vector and take that vector. Add them together. Remember how we add. We take it and we move it up, and then we connect from the origin to the end. And notice we get another vector on that line. When we take a scalar multiple of a vector on this line, by definition, we get another vector that's on that line. And you could prove this algebraically, right? Consider two vectors, x, which is x1 and x2, and take another vector, y, y1 and y2. So I have two vectors, I want to add them together. And I take the two vectors from this specific collection, whatever collection that is, however the m and b are defined. I know by definition that the x2 can be written as follows. It can be written as m times x1 plus b. And you'll notice that I can break this up into smaller vectors, so to speak, but let's not get ahead of ourselves. Anyway, the same deal here, by the way. If I have y1, this can be written as m times y1 plus b. So when I add them together, I get x1 plus y1. And on the bottom, I get m times x plus x1 plus y1 plus 2b, right? The b's are added together. So this is my new vector. Take out a 2 so that this is divided by 2 and that I have b here. And then I'll have 1/2 divided by this. Okay, and what I get, you'll notice, is if I were to let's say z equal 1/2 x1 plus y1, I can rewrite that vector as z, and you'll notice that I have a z here. So this is mz plus b. But notice the same m and the same b as I do here, which means that this vector of them added together also needs to be in this set, because this statement holds true about the second dimensional element there, or the element in the second dimension. So I just algebraically proved what we geometrically demonstrated, which is that if I take any two vectors on that line and I add them together, I'm going to get another vector that's on that line. Scalar multiplication is another easy one to show, right? If I have some vector, x1 and x2, the scalar multiple of that is just the kx1 and the kx2. And we know that by definition, I have x1 and mx1 plus b, but I multiply both by k. Okay. And here, what I end up having is the same deal. I have the kx1, I have the k, and I can take the k out of there and basically break it up. In other words, I can do some manipulations and I can end up forcing this vector to look like something in here. So anyway, the point is that when I take a scalar multiple of a vector on that line, I'm going to get another vector on that line. So what have we demonstrated? We've demonstrated an important property of, more generally, sets. So we say that for a given set A and some operation F that operates on the cross product of A and brings it back to A. In other words, given a set and given a function, we say that that function is closed if for all elements A1 and A2 in A, that the function applied on those two elements are indeed in the set A. So in the last case, I'm sorry, let me take a step back. Let me just be clear. We say that the operation is a closed operation if for any two elements I take in the set, if I apply the operation and I get back something in the set, it's a closed operation. If I don't get something that's in the set, if I get something that's not in the set, it's not a closed operation. Okay, so as it turns out, this is a closed op. This is for this specific set, we say that our operation is closed on the set. It's closed because if I add the two things together, the two vectors, I get a vector that's back in the set. If I come up with a scalar multiple of a vector, I get a new vector that's in that same set. There's some other properties that I'm not going to go through. There's a lot of them. But basically, the two most important ones we care about are addition and scalar multiplication. If that holds true for vectors in the real numbers, then we call whatever set it is a vector space. So a vector space is a collection of vectors. It's a set, such that if I take any two vectors in the set and I add them together, I get back a vector that's in that set. And likewise, if I take a scalar multiple of any vector in that set, I get back a vector in that set. So let's come up with another example of a vector space. Consider the set of all vectors to be x and 2x. Okay. In other words, it's all numbers here, x, in the real numbers, that I'm only considering vectors with some number in the first dimension and the second number is double that number. Is this closed? Okay, so here's how we show that. Take two vectors. We have vector x1, where we have x1 and 2x1. And we have another vector, x2 and 2x2. So I've taken both of these vectors, x1 and x2. Don't confuse these for positions. They're vectors, okay? x1 and x2 from the set A. So this is in A and this is in A. We know that's true because of how we defined the set A. If I add them together, I get the following. So the vector, the resulting vector is one such that the first number is a number in the real numbers, and the second entry is double that number, which by definition is how we defined A. So therefore, we know the result is an A. So we know that A is closed under addition. What about scalar multiplication? If I take a vector x such that I have x and 2x, if I multiply that by k, will I get the same thing? Well, let's see. We get k times x, and we get 2 times kx. And we know again by definition that this is a number, and this is double the number. And so therefore, this vector is also an A. So therefore, it's closed under scalar multiplication. And because it's closed under scalar multiplication and ordinary addition here, that the set A is therefore a vector space. Okay, we'll be getting much more into vector spaces in the following section, but before we do, I want to get to the geometric interpretation of a matrix.